Across human history, many ideas have been proposed to attempt to answer this question. But what is the actual physical rationale? At the end of the 19th century, Lord Rayleigh described the process by which the interaction of light with a neutral particle much smaller than its own wavelength causes its direction of propagation to change. This effect is known as Rayleigh scattering. It essentially works like this. The higher the energy of a given photon, the higher the probability that it will be scattered and change its trajectory. Knowing this, what can we tell about the color of the sky? Imagine a light ray from the sun traveling towards our planet. The more energetic blue photons end up being scattered and bouncing all over the atmosphere, end up coming at us from every single direction. The less energetic red photons tend to stick to their original trajectories, making the sun appear slightly redder. This reddening effect becomes more relevant as the sun gets closer to the horizon. In these occasions, the light has to cross a much larger thickness of atmosphere, which means that there are many more scattering opportunities for the photons. As such, blue photons end up being almost completely dispersed, making the sun appear orange and turning the sky to a reddish hue. This kind of scattering does not only take place in our own atmosphere, but happens all throughout the universe due to an effect called dust extinction. In this context, dust refers to microscopic particles existing in the interstellar medium within galaxies. If you look up at our own Milky Way, you might notice darker patches that obscure the rest of the galaxy. These patches are particularly opaque dust clouds. A dust cloud behaves a lot like our own atmosphere in the way it interacts with light. As before, blue light is strongly scattered, bouncing around the inside of the cloud. However, since we are observing from outside the cloud, this scattered light cannot reach us. All we see is light traveling along its original line of sight, which is now redder than when it was emitted. Astronomical objects are the benchmarks we use to test our cosmological models against. If we do not account for the dust scattering effect, then the conclusions drawn from their observation will be flawed. Galaxies will appear to be older than their actual age, and Type 1a supernova will appear to be farther away.
Gee, aren't we awfully far away?
Ow! All right, now pay attention.
While this might not seem too problematic, it can have long-spanning ramifications for cosmology. For example, the apparent discrepancy between different measurements of the Hubble constant has been suggested by some to be linked to an ill correction of dust effects. Despite being far from the only explanation, it is currently an hypothesis that cannot be ruled out, showing us just how little we know about dust and how much more we still have to learn. As to what happens if neither dust nor other systematics can explain the Hubble tension, that is a topic for another video.
If you enjoyed the video, like and subscribe. And don't forget, you ask CENTRAnswers.